Hi, welcome back to Econometrics B. We're still talking about multinomial choices, and now it's about identification. Okay, so identification is extremely important in discrete choice models, and it is extremely important because if you do not make identifying restrictions on the parameters, well, you're going to lose identification, and you'll not be able to estimate the model. Okay, it kind of arises from the issue that we don't really observe utility. Okay, we only observe whether utility is crossing a threshold, so that you choose, Coke instead of Pepsi or whatever the choice is. Okay, we don't observe the scale of utility. That's also irrelevant. You could scale up and down the utility. It's not going to affect what is maximizing utility. Okay, so that's essentially the same as you know for micro. You can take a positive monotone transformation of your utility function. You're going to get the same demand. Okay, you're going to get the same choice, not different in discrete choices. Okay, I'm gonna um, I'm gonna skip this slide. Okay, why don't we just get going? I think we know we need to deal with identification problems and impose restrictions. And you remember that we were making the scale normalization in the probit model, setting the sigma equal to 1, and so on and so forth. Okay, the question is, what are the potential identification problems in the random utility model, and what are the ones how are we going to deal with it? I'm going to start with actually a binary example, but the idea here actually it kind of generalizes to multinomial examples. It's the same logic, and I just think it's good to look at what is the type of variation that's kind of driving what we can identify. Okay. So here's a small little model of transportation mode. It's kind of made up model. You got the utility of choosing a car. So this is C here means car, and then you have the utility of say taking the train. That's another utility, and then you got alternative specific constants. So coefficients that varies across the alternatives. One for car and one for train. And then you got alternative specific constants on that variable that varies over the alternatives, namely the price. Okay, maybe the price of taking the car is different from the price of taking the transportation mode train. And then we have the variables. These are the type of variables that enter into the multinomial logic. Remember, we have alternative specific coefficients on these variables. This is like income, which would be like only on individual specific. Okay, I've dropped all the subscripts I, but let's just say that this varies with I, and potentially also the prices would vary with I. It actually make a difference if in terms of whether you can separately identify these two effects. Anyway, so and then you got your error term. Okay, that's also an error term. That's one for each alternative, right? So these are like taste shifters. Some people just prefer cars, or other prefer train, or maybe there's some idiosyncratic train reason. The train is delayed, or maybe you don't want to take the car because it's snowing. Things that varies over time, or it could be individual specific. That's kind of that's our model. Okay, now let's talk about what we can identify here. Okay, from observing choices. Okay, observing choices together with prices and income. Okay, so here's the random utility. We have the decision rule is for choosing car, is that if you choose car, well, then the utility difference must be positive. Otherwise, you will choose the train. Okay, and then we can just calculate that utility difference by subtracting these two equations from each other. And then basically, I've collected the alternative specific constants. Try to put stuff in brackets that could be moved outside. So here the constants, well, they're together then, but here the price, or the coefficients of the price, we cannot put that under the same bracket and put price outside, because price in itself varies from car to train. Okay, so but we can do that for essentially for income. And then you see here you got the coefficients on income for car and for train, put outside the bracket, and then you got the difference here in the alternative. So So then we have what we observe is, y if car is chosen, 0 if train is chosen. So it looks like here that what we can identify, if we were to estimate, put the, let's organize all these different coefficients here into a vector, then what we could identify is really only, if you look at it here, the difference in the alternative specific constants, the difference in the alternative specific coefficients on income, whereas you could identify separately delta C and delta T separately, okay? So, and if you put them into this parameter vector, you get something like this, and then you get like a vector of explanatory variables that will be like the constant, and then the price of car, the price of train, and then the individual, and then you got like a difference in the error term. Say, suppose this is normally distributed, we could estimate this by appropriate. If each of these are at extreme value, well, then the difference is going to be logistic, and we could estimate this model with essentially appropriate, and kind of using our latent utility difference approach. Okay, so we get something like this is our latent variable. Okay, so then like if this was normally distributed, well, then you could do like appropriate of y on x and estimate each of these 4 coefficients. But from these 4 coefficients, well, we cannot learn about the coefficient on car and the constant on car and train separately. We can only learn about the difference between them. Okay, so and then above and over and above this problem, we have the issue that we can only identify beta relative to the variance of this error term. So we have the usual issue with this with the scale normalization that we need to make. Okay, so we usually, if it's appropriate, normalize the variance of this guy to 1. Okay, so that's kind of a repetition in some sense. But the new thing here is we are specific to what those different types of coefficients are, things that potentially vary across, vary depending on whether the variable is varying across alternatives or not varying across alternatives. For coefficients that varies across the alternatives, well, what you can actually identify is only the difference between them. Okay, so here you would need to make a normalization if you were to do like a multinomial logit, for example. Then that, if you make that normalization that the last alternative is 0, which is essentially what we are doing if we are estimating a probit of y on x, that would be like saying in a random utility framework that the utility associated, the utility, net utility associated with train is 0, right? Then we would, our coefficients would mean basically the coefficients measured relative to that outside alternative that we have normalized against. Okay, so here's another way to see the same thing, and it becomes more specific. And let's look first at the conditional logit model, and then look at the multinomial logit. First, about the constants, right? So you cannot have a constant in the conditional logit model, right? You cannot have a constant, and actually we should have added that right here, just a constant that doesn't vary across alternatives. Where would that go? That would have been difference away here. Okay, you can see that directly here also in the logit formula. If you put a constant that's not varying across the different alternatives into conditional logit, well, it's going to appear here in any other alternative. You can put this outside the exponential. You know, the sum, the exponential of the sum is the product of the 2 exponentials, just like we have here. And you do that down here. And since this is the same across all the different alternatives we're summing over here, well, it's just going to be, you can just, divide through and then it disappears. So if you put in a constant that's not varying across alternatives, it's going to disappear. Okay, so we cannot have constants that does not have any alternative specific variation in the logit model. You can have a alternative specific constant, and then you can normalize one coefficient to 0, or to some value, and then you would be able to identify the rest of them. But you cannot have one common constant. Bottom line is you need to have variation across alternatives to identify anything. Okay, so here our solution is to put the intercepts to 0, and it doesn't matter. It doesn't change the choice problem. Otherwise, it's possible to shift all utilities without changing the probabilities, and therefore also without changing the likelihood. So we cannot identify that. And it's not a problem, right? Because we don't really care about the overall level of utility. Okay, it's kind of an abstract construct in the first place. Okay. For the multinomial logic with a similar problem, you add a constant, okay, and now the constant then is multiplied with x, okay. So if you do that, since x is not varying over the alternatives, it's going to be the same xi delta that you have inside, that you can put outside here. So again, you divide through and it disappears. Okay, this means that you need to fix the scale, or sorry, not the scale, the level of those coefficients. Essentially, you can if you add like 100 to all coefficients on beta, it doesn't change anything. Okay, what matters is the difference in the coefficients across the different alternatives. Okay, so you need to make some normalization here, and what we usually do is that we normalize the first one to 0, or some alternative that you want to look at, you normalize that to 0. I'm going to show you an example of multinomial logit of three different status in the labor market, schooling, working, and staying at home. And there we can normalize against the alternative that we wanted to. Okay, and you would get different coefficients, but it would predict the same thing. So this normalization and identifying restrictions implies that coefficients are always measured relative or with respect to some baseline cap. Okay, that we set equal to 0. In mixed logit, or the combined logit that has both multinomial and conditional part, it's affected by the both problem, and the coefficient solution is fix basically coefficients of a baseline categories to equal to 0. And by the way, one thing that is necessary to do is that we need to basically, it's the entire vector of coefficients for x. So if you have k exponential variables, you need to make k restrictions. It's all the betas for all the alternative, not for all the alternatives, but for all the different exponential variables that you need to normalize. It's not just one normalization, many normalizations, one for each parameter. Of course, in nonlinear models, it's not like it's not necessarily like this. It could be that the nonlinearity of the utility function would allow you to identify more parameters without making all these scaling things. But what you do need to make sure is that there is a reference alternative that has a fixed utility in some sense, at least for each individual. And then how you do that, well, that's kind of changes interpretation of the coefficients. So here the solution is really just drop in the combined logit or mixed logits, drop all fixed intercepts across all alternatives. Make sure also to make of course the scale normalization of the which is already in place by the logit model, where there's no variance parameter, but otherwise if there is one, well, you need to normalize at least one variance or normalize at least one parameter to be fixed. Okay, so like for example, it would be natural to in the probit model to have like a one variance being equal to 1, for example. So again, here that's scale of utility. That's irrelevant, right? So I just repeating myself a little bit, just showing that it's the same thing in the multinomial logit as we've seen previously in the binary probit model. You multiply that error here with some scale factor that scales up the variance. Okay, now then the implied conditional choice probabilities, well, they're going to be logit. If you divide everything through here with sigma, then they're going to still be I extreme value type 1 distributed with the usual with that variance that has. So then you divide that through here and you get, beta divided by sigma, and that doesn't change the maximization problem, so you get the same choice probabilities. Now all coefficients here are just normalized with beta. And again, you have the same problem. You can scale up the variance and scale up that betas, all the betas, you get the same response probability. So what you usually do is you fix that that scale parameter to B1, okay? And it doesn't change the fit of the model. Otherwise, you would not be able to obtain the parameter estimates. So here's a key takeaways on identification in multinomial or discrete choice models that are unordered, is that the scale of utility is essentially irrelevant. Okay, only that's one thing that's about this guy here, that scale of utility is irrelevant, and then only differences in utility matter, differences across alternatives. So these are like the two key things you have to keep in mind. Regardless of how complicated your model is, these things have to hold. Okay, so that's for sure. Okay. Now, okay, so we want to move on and talk about some features of interest. What do we actually want to make predictions about? That's what I'm going to talk about in the next video.